everyone, and welcome to the Learning Space workshop on the Doppler Effect. Today we'll be building on your knowledge that you would have learned before in waves, sound, and light. The Doppler Effect, as depicted on our screen, describes the change in frequency, the pitch of the sound detected by a listener, because the sound source and the listener have different velocities relative to the medium of sound propagation. Practically speaking, when you have a stationary object that is emitting a sound, when it is not in motion, the sound waves around this object have the same frequency and the same pitch in both directions. This is in comparison to when you have a moving object which is emitting a sound, in which case, when the object is moving away from a certain position, relative to that position, the wavelength of those sound waves increases, the frequency of those sound waves decreases, and the pitch of those sound waves decrease, as depicted over here. On the other hand, when you have your source of sound moving towards an object emitting a sound, relative to the position towards which the source of sound is moving, the wavelength of your sound waves decreases, the frequency of your sound waves increase, and the pitch increases. Okay, awesome. Let's take a closer look at sound waves. We have been given this wave equation in which the velocity of the waves, the sound waves, is equal to the frequency of those sound waves multiplied by the wavelength of those sound waves. This means that, according to your knowledge of proportionality learned in previous years, as the frequency of the sound waves increase, so does the velocity of the sound waves. The velocity of the sound waves is also directly proportional to the wavelength, and the frequency of the waves and the wavelength of those waves are inversely proportional. Let's put this formula into practice. Say we have waves moving at a speed of 343 meters per second with a frequency of 200 hertz. We can calculate the wavelength of those waves by plugging these values into this formula. V is equal to F lambda. By doing so, we will get an answer 343 is equal to 200 lambda. And if you calculate that, lambda being equal to 343 divided by 200, you'll get an answer of 1.7 lambda for your wavelength. Let's do another example where we don't know the frequency, but we have wavelength and wave speed. If the speed of the wave is equal to 343 meters per second, then, and we know that the wavelength is equal to 3 meters, our frequency can be calculated by dividing 343 by 3, which gives us an answer of 114,3 hertz. Let's do a final example where we do not know the wave speed, but we do know the frequency and wavelength. We'll just plug those two values into our formula. So the speed of the waves is going to be equal to 9,000 in this case, multiplied by 3 times 10 to the power of negative 2. Therefore, the velocity of those sound waves is going to be 270 meters per second. And that is our wave equation. Let's move on to putting our Doppler effect into practice. As you can see, here we have our Doppler formula. And we've been given the above scenario. A police car approaches a crime scene at 20 meters per second, where the listener is waiting. Its siren emits sound with a frequency of 1600 Hz. The speed of the sound in air is 343 meters per second. All right, let's begin to fill our values into this table. V in this instance is going to be the speed of the sound wave in its medium of sound propagation in air, which we've been given as 343 meters per second. Vs is the velocity of the source of the sound, and we know that this is going to be 20 meters per second. VL is going to be the velocity of the listener, and we know that because the listener is waiting, they're stationary, their velocity is going to be 0. Okay. Fs is the frequency of the sound emitted by the source, which we've been given as 1600 Hz. And Fl is what we do not know, which is going to be the frequency of the sound experienced by the listener. Now we know that this police car is approaching the scene at 20 meters per second. What does that imply? It means that the frequency of the sound waves being experienced by the listener is going to be greater than the frequency of the sound waves emitted by the source. How will we account for this in our formula? We are going to say FL is equal to V plus VL is going to be 0 over V plus Vs. And that is going to give us, apologies, V minus Vs. That is all multiplied by the frequency of the sound emitted by the source. Why have I subtracted Vs in the denominator of this fraction? Because we're creating a top-heavy fraction. The result being that the frequency of the sound experienced by the listener will be greater than the frequency of the sound emitted by the source. Why is that happening? Well, thinking back to proportionality, looking at this formula, we can tell that if this value is increasing, the frequency experienced by the listener is going to be directly proportional to that. Plugging our values into this formula, we are going to get FL is equal to 343 over 343 minus 20 multiplied by 1,600. Okay. And that's going to give us a final answer of 1699,1 Hertz. Now that you've seen me do one of these examples, I'd like you to pause and attempt this example. Find the unknown value or the missing value in the scenario and fill it in this table. Go ahead and try it. Okay, now that you've had an opportunity to attempt this example, let's see how you did by doing this together. We've been given the scenario that a listener is cycling away from a car that is stuck at a red light. The driver blows his horn out of frustration. The listener hears a sound with a frequency of 2,600 Hertz and the car emits a sound of 2,700 Hertz. The speed of sound in air is 339 meters per second. Let's go ahead and fill in this table. We know that V, the speed of sound in air, is 339. Vs, which is the velocity of the source, is going to be 0 because the car is stuck at a traffic light, it is stationary. VL, we have not been given any information about, so that is a missing piece of information you would have had to find. Fs, the frequency of sound emitted by the source, as we know, is 2,700 Hertz. And FL, the frequency of the sound experienced by the listener, is going to be 2,600 Hertz. Let's fill these values into the formula to figure out VL. frequency experienced by the listener is going to be 2,600. That is going to be equal to V, which is 339, minus VL over V, 339, multiplied by Fs, 2,700. Okay, and when we isolated for VL, you will get a final value that VL is going to be equal to 26 over 27 multiplied by 339 minus 339, or multiplied by -1, which will give you a final value of 12,6 meters per second. Okay, let's try a second example. I'd like you to pause and attempt to do this. Answer both questions A and B. Go ahead and give it a try. Great. Okay, let's see how you did by doing this together. Our scenario is that an ambulance is approaching an emergency room where a nurse is waiting for it to arrive. The siren emits a 1200 hertz sound, and the ambulance is traveling at 110 kilometers per hour. The speed of sound in air is 343 meters per second. The first question they've asked is, will the pitch of the sound heard by the nurse increase, decrease, or remain the same? And the answer is that the pitch of the sound will increase because the ambulance is moving towards the nurse. Question B is asks us to calculate the wavelength of the sound observed by the nurse. And to do that, we're going to use our Doppler formula. We're going to say the frequency of the sound experienced by the listener is equal to the velocity of the sound in air divided by the velocity of sound in air minus the velocity of the source of sound multiplied by the frequency of the sound waves emitted by the source. Plugging our values into that formula, the frequency of sound experienced by the nurse is going to be equal to 343 divided by 343 minus R. The speed of the ambulance we've been given is 110 kilometers per hour, and we know that we need to have it in meters per second, so we're going to convert that and get an answer of 30,6 meters per second. So that's 343 minus 30,6. And that is all going to be multiplied by 1,200. Therefore, our final answer, that is the frequency experienced by the nurse, is going to be equal to 1317,5 hertz. And they've asked us to give them the wavelength of the sound observed by the nurse. And as we know from earlier, the speed of the sound in air is equal to the frequency of the sound multiplied by the wavelength of that sound. And as we got the information that the speed of the sound is 343 meters per second, that is going to be equal to the frequency 1317,5 multiplied by the wavelength, which we are looking for. Therefore, the wavelength of the sound is going to be equal to 343 divided by 1317,5. And that gives us a value of 0,3 meters. All right, now that we have done some practical examples with Doppler effect, let's move on to Doppler effect and light. Now, you will recognize this light spectrum from your earlier studies in wave, sound, and light. And we know that on this side of our spectrum, you have a shorter wavelength and a higher frequency of light. And on this side, we have a longer wavelength and a lower frequency. Applying Doppler to this means that when you are moving away from something, or when light is moving away from you, you will experience a red shift. That is, longer wavelengths mean that the light will shift to the red side of the spectrum. Whereas, where light is moving towards you, you'll get a blue shift. And that is because the wavelengths are getting shorter and our frequencies are getting higher as the source of light moves towards you. So what is the relevance of that red shift, blue shift theory? Well, scientists have discovered that light from distant stars experiences redshift, and that is evidence of an expanding universe, which is where we get our Big Bang theory from. And I think that that's just an interesting side note of the practical effects of, or the practical applications of Doppler effect. Further practical applications of Doppler is in ultrasound, where ultrasound imaging uses the slight differences in the frequencies of the echoes of waves, which happens due to Doppler effect, to construct a picture of the internal organs. And that is the end of our workshop on Doppler effect today. I hope you enjoy the rest of your day and good luck with your studies.